So, welcome back. So, again we will continue a discussion on Fourier transform. So, if before move on to some properties of the Fourier transform. So, just one example. So, this f of x is the characteristic function of minus 1 1. So, it is easy to compute the Fourier transform of this function. Okay, so, this is just sin j by j, which is 1 when j equal to 0. Okay, so, this is a bounded function, it is continuous and bounded, and it also goes to 0. So, that is fine. But important thing to notice is this is not an L1 function, okay, but it belongs to L2. So, if you have not done this thing, so you do it. Okay. So, later on we will because it belongs to L2. So, we have a way of computing its this integral sin j by j square. So, later on when we study Plancherel theorem and Parseval relation, so there is a relation between this integral and the L2 integral of the function f itself. Okay. So, that will come back, okay. But for the time being you can just do this computation and verify that this f cap is given by this simple. More generally you can take any interval, finite interval, and compute its Fourier transform. Okay. So, some simple properties. Okay. So, these are directly from the definition. Very easily verifiable. Okay. So, this the first one. So, if I consider, so again that f is in L1. Okay. So, just let me not write it all the time. So, just you define this. So, scaling, dilation. Okay. So, what is the relation of the Fourier transform of G and Fourier transform of f? So, this very easily doable. So, this is lambda to the minus n f cap of j by lambda. Okay. So, once you know the Fourier transform of a function, all its dilations can be worked out. Okay. So, next one is the translation. So, if okay, put f a of x is equal to f of x minus a. So, a is a fixed number, fixed element in R n. Okay. So, this is just translation. So, then f a cap is e to the so, I am putting x minus a, and then when you change the variables, so you get minus I a dot j f cap j. Okay. So, an exponential factor appears. Okay. So, again very simple properties. So, this Fourier transform is a linear operator Fourier transform is linear, that is because of the integration. Okay. So, sometimes we write this as this f. So, this is from as of now. So, it goes into L infinity, linear and continuous. Okay, that already we have seen continuity. So, f of f in L infinity is less than or equal to some constant. So, this is the continuity. This we have seen it. Okay. In addition, this Fourier transform vanishes at infinity. Okay. So, one of the important things we need even later. Okay. So, let me just state it as a theorem. So, let me state this for general R n, but let me just try to give proof for n equal to 1. If f is in L 1 and x j f is also in L 1, then del f cap by del j exits and equal to let me I think minus minus I x j f cap. Okay. So, let me sketch the proof in n equal to 1. Okay. So, this is an important result. Okay. So, it tells a sufficient condition under which the Fourier transform is differentiable. Okay. So, n equal to 1, let me take that. So, how do you show that a function is differentiable? So, you take as usual the different quotients and try to prove the limit exists, right. That is what we do, right. And this proof also tells many things. So, how that the powerful results from integration theory, namely the dominated convergence theorem and other things. So, which are used to interchange the limit and integral sign. Okay. That is what. So, we want to take this is given by an integral and you want to take the limit of this thing, and then that limit we want to push under the integral sign, and that is allowed by the dominated convergence theorem. So, please go through these things carefully because we may not stress this all the time, understanding that you know all these arguments, but they are important, and okay, for rigorous study of the subject you have to do that. Okay. So, let me just forget that 2 pi n. Okay. So, because I may forget at many places. Okay. So, just so this f x. Okay. So, let me write that e to the minus I x j plus h, right, minus e to the minus, this is just from the definition. Okay. Since I am working only in n equal to 1, so this is just product of real numbers. Okay. So, let me do simplification here itself. So, just you please write down all these steps carefully. So, this is e to the minus I x j. Okay, so this e to the minus I x h minus 1 by h. Okay. So, I am just writing this. So, what about this one? So, we can just write that e to the minus I x j. So, e to the minus I x h by 2 into sine x h by 2, okay, maybe at 2 I, okay, some factor 2, okay. So, some constant, let me write that, this is h. Okay. So, these are in modulus they are 1, so they do not create any problem here. And what about this one? So, this is whole thing is bounded by some constant mod x. Okay. And by hypothesis, so since we are working only with n equal to 1, so this x f x is in L1. Okay. So, the integrand is bounded by mod x into f x in absolute value. So, and that is an L1 function. And what happens when h tends to 0? H tends to 0, just look at here. Okay. So, that will produce just an x. Okay. So, the whole thing. So, this. So, I am using dominated convergence theorem. So, fill in all the details here. So, you the important thing is we have to keep track of. So, this is for the estimate, but just look at the factor here. Okay. So, this tends to, as s tends to 0, so we get minus I x as h tends to 0. Okay. So, another comment I wish to make here. So, usually when we apply dominated convergence theorem, we always take sequences. Okay. But whereas here we are taking h as a continuous variable. Okay. The same argument we can do by taking any sequence tending to 0, and since the limit is independent of the particular sequence. Okay. So, this applying dominated convergence theorem certainly makes sense. Okay. So, this integrand tends to minus I x f x e to the minus I x j, and it is bounded by an L1 function. So, by dominated convergence theorem, so this goes to minus I 2 pi minus n by 2 x f x e to the I x j, and that is as s tends to 0. Okay, and that is precisely minus I x f hat. Okay. So, in general, when you want to study in Rn, so you just take j h e j. Okay, instead of h you take h e j. So, in that direction. Okay, so same proof works for that. Okay, so this is an important thing, and so now you can iterate this. So, if there are more powers, so you are getting more derivatives of the Fourier transform. Okay. So, there is so this is for the multiplication of the function f by a polynomial, okay, so to speak. So, what if f is differentiable and also that derivative is in L1, okay. So, that is the next result. I just want to so just remember to write, because we are okay, just remember to fill in all these details. So, there are several steps here, and convince yourself how this dominated convergence theorem is used. So, this always used in interchanging the limit and integral sign, okay, and under appropriate conditions. So, we should verify those conditions. Okay. So, suppose f and f prime, okay, again let me just state it in n equal to 1. So, e.g. So, L1R, then so now I can take the Fourier transform of the derivative. Okay. So, in this course we are talking several notions of derivative. So, for the time being here, this notion, this f prime means, okay, so it is almost everywhere definition. Later on we are going to talk about weak derivatives, and they are different. Again we will come back, okay. So, this is not the end, we will come back, and in what sense. So, this is almost everywhere. Okay. So, essentially if you look at the definition of the Fourier transform, it is here. Okay. So, if I want to take the replace f by f prime, and essentially I want to integrate the parts, okay, and that is in the whole domain. So, let me not go into that, but let me just give you a heuristic argument, but you should work out the details properly. Okay. So, because this is also an important result. Okay. So, let me again start with this f of x plus h minus f x. So, this is for h naught 0, okay, and your f prime is here, and there is a limit, right. So, this. So, now you take Fourier transform. So, this is okay. So, we have already seen that this is just translation. So, that gives me minus I h j, this is just minus 1 by h, and this is just f cap j. And since we are assuming f prime is in L1, so that gives me, okay. And as h tends to 0, what happens? So, this gives me this is minus or plus, I just check this, this may be plus. Okay, so this gives me Ij as h tends to 0. Okay. So, but several integrations are not written here. So, essentially you want to do that, okay? And so you work out the details. So, this, that is what you get. So, essentially I have not said anything here, but just a heuristic argument, you work out the details. So, let me just write this in general formula, so to speak. So, this so later on we see many examples. Okay. So, more generally, so as of now we are considering only the Fourier transform of L1 function. So, I assume all these functions whose Fourier transform we are taking are so I mod alpha j alpha. So, this introduce we have introduced this notation. So, this f cap j. So, all multi indices alpha. Okay. And then the that converse part. So, if I take polynomial and the function and then its Fourier transform is minus I to the mod alpha d alpha of f cap. Okay, again this. So, you just iterate them, okay, assuming that all these functions are in L1. Okay. So, one important function I just mentioned. So, the example. So, you should work out. This I am going to use repeatedly. So, this phi x e to the minus mod x square by 2. Okay. So, you can actually do the computation, hard computation. Okay. So, this is one function whose Fourier transform is itself. Okay. So, let me give a proof of this thing using ODE. Okay. So, if you look at phi satisfies this linear ODE. Again, let me take n equal to 1. Okay. So, for n bigger than 1, so this phi x we can write it as phi of x, okay, not phi, but okay, let me write phi 1 x 1, phi 1 x 2. So, we can write it as product of n functions, each function being a function of only one variable. Okay. And so, the integration is also one dimension. So, this is sufficient. Okay. General case follows by this writing like that. So, for n equal to 1, phi satisfies this ODE. Okay. So, phi prime is minus x prime. So, that is, and phi 0 is 1. Okay. And now you take the Fourier transform of this, okay, Fourier transform of that. So, and use this property just written here. Okay. So, what happens if you take the the derivative of the Fourier transform. So, you also see that it satisfies the same equation. So, let me again just write that. So, here we are just using these properties of and this is a very nice function. Okay. So, it is not only in L1, its derivatives are in L1. If we multiply by any polynomial. So, later on we introduce that class. So, this belongs to that very nice class. So, if you multiply phi by any polynomial, that is also in L1. Okay. So, we are just using these properties to derive this. Okay. So, only work we have to do is phi cap 0. Okay. So, this is a Gaussian integral. So, you do it. Okay. It comes in terms of the gamma integral. So, this is the only work we have to do here, Gaussian integral. Okay. So, what is this one? This, if you write using the definition, this is just over r e to the minus x square by 2 dx, and that is 1. Okay. So, that very important integral. Okay. That is 1. So, phi and phi cap both satisfy the same equation with same initial condition. So, uniqueness implies uniqueness of solutions of ODE implies phi equal to pi. And as I said, the general case of n follows from this observation. Okay. There. Okay. Just want to. Okay, I will discuss that only after the inverse transformation. So, let me directly go to inverse formula. Okay. So, here I am going to use this phi x explicitly. Okay. Okay. The full derivation of this inverse formula is technical and lengthy. So, many steps I will be omitting, but you just so what's first involved, let us see that. So, in fact, this course is about triggerization of such formulas. Okay. So, here, so suppose f and f cap both are in L1. Okay. So, as such I can take the Fourier transform of f cap, and do I get f my f back. Okay. So, let me just state that inverse formula. So, put g of x, okay, again that factor So, this certainly I can define. So, there is no problem at all. E to the I x j d j. Okay. Since we are assuming f cap is in L1, so this certainly this integral makes sense. So, only change here is the change in the exponential sign. So, instead of minus we are taking plus, but everything. So, g is again continuous, bounded. Okay. So, all those things continuous, bounded, etc. all those things can be said because f cap is in L1. Okay. So, what is the relation between g and f? Question. Okay. So, let us write this because we know the formula for the f cap. So, just so there is another factor there. So, let me put that here. So, e to the I x j. So, let me just write that. So, there is already an x. So, let me use some other variable here. So, this is y j dy. Okay. So, if we can justify the Fubini theorem in this case. Okay. So, suppose it is possible, I am not saying that it is possible, but just let us say it is possible. So, f of y dy and then e to the I, what we get, x minus y dot j dj. Okay. So, as of now this we cannot make any sense out of this, but as we develop the new theory of distributions and tempered distributions, indeed this we can give a meaning to this along with this factor, as again the Dirac delta function comes into play and we do get. Okay. So, again arguing like Dirac, so this we do get fx. Okay. So, this is the purely heuristic argument, no justification of interchange of integral and this meaning of this integral. Okay. So, it as of now it appears everything absurd. Okay. But by putting proper factors, okay, so those are auxiliary functions, we can make sense out of this. So, something going to 1 we have to put here, something going to 1 essentially, and make sense out of all these heuristic computations. Okay. So, we do expect, certainly we can define this function. Okay. And we do expect this g to be our f. So, we are getting back f, but it requires some work. Okay. So, let me just okay, it's it's a lengthy calculation. So, let me stop here and I will take up this inverse formula in detail next time. Thank you.